So our next speaker is Professor Yuejie from Carnegie Mellon University. Yuejie, can you start sharing the screen?
Sure. Let me see how to do it.
Yes. So Yuejie has done many great works on the theoretical and algorithmic foundations for machine learning, inverse problems, and non-convex optimization, particularly by exploiting sparse and low-rank data representations. More recently, she also has works on reinforcement learning, which is also part of the topic of her talk today. So Yuejie has won numerous awards for her research, including the Presidential Early Career Award for scientists and engineers from the White House, as well as many other awards from NSF, Air Force, ONR, Google, and so on. And very recently in 2019, she received the inaugural IEEE Signal Processing Society Early Career Technical Achievement Award for her contributions to high-dimensional structured signal processing. So with that, I'm really excited to hear more about her recent work. So thanks.
Okay, thanks so much for the kind introduction. Thank you so much for having me in this wonderful workshop. Today, I'm going to share a little bit about our recent work on using preconditioning to achieve faster convergence in statistical and reinforcement learning. So I don't think I need to really motivate non-convex optimization. This is kind of the theme in this workshop. Most of the problem we've seen today can be solved as non-convex optimization, where the goal is try to estimate some parameter interest by optimizing certain loss function of interest. Okay, so often non-convex problems are NP hard in general. Even for very simple neural network structures such as one-layer neural network, we know there are data configurations where there can be exponentially many bad local minima, and this typically give very pessimistic problem to solve from the classical optimization perspective. Despite so, we know that in practice, people are never afraid of non-convexity. They can solve this problem on a daily routine. Really the key challenge here is how to reconcile this practice from the theoretical perspective. In recent years, there has been a line of work from many communities where sort of the underlying key idea is rather than just worrying about the worst case scenario, most of the time the data we deal in practice can be sort of as much more benign and can be sort of as random generalization from certain statistical model beneath. And once we have a statistical model, we can leverage tools such as concentration and the law of large numbers so that instead of by just reasoning about the worst case, we can think about on average what the loss function might look like. And it turns out that on average, the function can actually carry much more benign properties, such as no bad local minima that you heard in some of the previous talks. And given so, this nice landscape in the average case, we've seen that even for very simple algorithms, they can be pretty efficient for non-convex learning. And one of the algorithms we'll be looking at in today's talk in particular is just vanilla gradient descent or gradient descent in general, where you simply update your parameters by searching along the direction of the negative gradient. All right, so we've seen the success of this kind of statistical learning in a lot of works in recent years. I tried to record a large number of them, but I think I became lazy and didn't stop updating this probably sometime around last year. And this is a highly incomplete list of the existing work in this literature. But this gives you a sort of a impression how basically the successful effectiveness of this line of thinking has been in generating provable non-convex optimization algorithms. All right. So the goal of today's presentation is try to move one step further along this line of thinking, particularly try to improve upon the computation efficiency of vanilla gradient descent. So we know that vanilla gradient descent, despite all this nice sort of global convergence guarantees that we can achieve even for some challenging non-convex problems, the computational efficiency tends to slow down, particularly when the underlying problem becomes ill-conditioned. Okay, the purpose of today's talk is to highlight the role of preconditioning. We want to argue that if you can design preconditioners that very carefully so that instead of search along simply the gradient direction, search on some preconditioned gradient direction. And you can actually achieve much better convergence without incurring a huge computational loss. So in some sense, you can still maintain the low computational cost of vanilla gradient descent per iteration, but converge much faster. Okay. Now, in this presentation, I won't be able to develop a sort of unified theory that shows this for the entire universe of non-convex problems. That is just too ambitious, could be potentially my entire career goal. But I just want to show two case studies that we have been doing recently in my group with wonderful collaborators. The first problem is on try to accelerate low rank matrix estimation in statistical learning. And another problem is try to look at doing policy optimization in the context of reinforcement learning. All right, so let me start with the first story on accelerating yield condition matrix estimation. This is joint work with my student Tian Cong from CMU, and also my collaborator Cong Ma, who's currently doing a postdoc at Berkeley, but he's going to join University of Chicago as a tenure track assistant professor in the coming fall. All right. So low rank matrices are a ubiquitous object in data science. Broadly speaking, the data matrix is low rank because we can explain the entries using only a small number of latent factors. It has many applications in imaging problems such as radar imaging, hyperspectral imaging, to problems in recommendation systems, social network data analysis, bioinformatics, and so on. As a sort of a standard prototypical problem in today's presentation, I'll be particularly looking at the problem of low-rank matrix sensing, where there's some underlying matrix M of dimension, say, A1 by N2, which is very large, but the rank of this matrix is very small, let's say called R. And typically we have some imaging devices, which is modeled by a linear map A in this particular talk. This can be a, say, MRI device, it can be some other sensor suits that you have. And you're going to collect a bunch of measurements, the M measurements, through this linear map, potentially corrupted by noise. Particularly of interest in inverse problems is that we care about the regime that we call the sample stop regime, where the sensing budget is typically much smaller than the ambient dimension of this matrix that is N1 by N2, but just barely larger than the degrees of freedom this low rank matrix on the order, say, N1 plus N2 times R, if you count the number of unknowns by leveraging the low rank structure. All right, so in order to solve this problem, we have to capitalize this underlying low rank structure. And one natural objective function is just to search for underlying matrix of rank R that minimize the squared measurement residual. Okay. This formulation nonetheless has two issues. The first one is this rank constraint is NP hard. The other issue is we are still manipulating this large matrix in the ambient dimension, which can have very high memory and computation cost. Appealing idea is to directly leverage this low rank structure by invoking its low rank factorization by writing it instead as a multiplication of two skinny matrix factor X and Y. All right, so by doing so, I end up to have an unconstrained optimization problem over the matrix factors X and Y, so that I can directly now just optimize over this skinny factor that are typically more computation and memory efficient. But nonetheless, this problem is extremely non-convex because obviously I cannot uniquely identify these low rank factors up to some invertible transforms. So this problem is non-convex in general. Right? So from the theoretical perspective, reasoning about the convergence guarantee of this problem becomes more challenging. Despite the challenge, there has been a nice line of work in the prior art that try to solve this problem with theoretical performance guarantees. So I'm going to just illustrate one particular approach using gradient descent, where instead of directly optimizing this unregularized loss function I just wrote down in the previous slide, in this previous line of work, people often try to first regularize this loss function using this so-called balancing regularizer. If you look at the form of this regularizer, this does nothing but try to balance the norm of the two factor X and Y so that you can effectively constrain the ambiguity group to just orthonormal transformations. And with this in place, often the objective function has somewhat a nice landscape, as I show here. Roughly speaking, around the ground truths of interest that you often can sort of locate a nice local neighborhood that we call the basin of attraction. And within this basin of attraction, the function typically has a nice convex function-like property, or strong convex function-like property, so that as long as you can get a good initialization, let's say a spectral initialization, that I won't get detailed into in this presentation, but just have to ask you to trust me, this initialization indeed worked pretty well. And once you do this initialization, you can simply run vanilla gradient descent type of updates to update the low rank factor matrices using this very simple vanilla gradient descent type of search. And indeed, one of the nice early theory for this algorithm says the following, quoting this paper by Tu et al., that if you have indeed a low rank matrix that has a condition number kappa, which is simply the ratio of the largest non-zero singular value divided by the smallest non-zero singular value, then for this low rank matrix sensing problem with IID Gaussian design, we know this algorithm will achieve linear convergence, meaning that you can achieve epsilon accuracy as long as you run this vanilla GD with the other iteration on the other log one, where epsilon, where you incur a pre-constant that is on the order of the condition number kappa. Okay. From the statistical perspective, this algorithm will work as long as the sample complexity is just a little bit larger than the degrees of freedom of this problem. So overall, this algorithm achieves both near optimal performance in terms of both computational cost and statistical cost. Right? And indeed, similar type of results have been established for many other low-rank problems in the literature, which I don't have time to get into, but they all share some with a similar flavor. Right? Now, since the result is already pretty nice, what do we want to focus on in today's presentation? I want to particularly draw your attention to the computational cost of this algorithm, in particularly its dependence with respect to the condition number. In particular, on this slide, we just show a simple toy example for matrix completion, where you see if I keep all the factors to be the same, but only perturb the spectrum of this low rank matrix from a condition number to the ideal setting with 1 to say up to 20, you see the convergence of this algorithm indeed slows down as you increase the condition number. So this just means that the previous computational dependency on the condition number you see is not an artifact of the proof, but actually inherent to the actual performance of this vanilla gradient descent algorithm. And in many practical scenarios, condition number can be very large. I won't get into all the possible applications, but I just want to highlight a typical example, drawing a real data example. So on this slide, we show a particular real data set on cluster concentration level at 120 water junctions measured over 180 time slots. So you can imagine this gives a data matrix of size 120 times 180. And just like many of the other type of big data problems, the spectrum of this matrix actually enjoys this nice power law decay. Verifying this matrix indeed can be well approximated by a low rank matrix. Right? So if I want to approximate this matrix using a rank 5 matrix, which captures about say 88% of the total energy, you end up having a matrix of rank 5 of condition number 20. Right? Now, if you try to capture a little bit more energy by using a rank 10 matrix approximation, the condition number is even larger, around 60. Okay, so you see that even with this nice data set, the condition number can be already very high. That is, give you some non-negligible number that will really slow down the convergence of the algorithm. All right, so with this in mind, a natural question is, then can we accelerate the convergence of vanilla gradient descent to iteration complexity that is independent with the condition number? Particularly, we want to focus on gradient descent type of algorithm in the sense just to maintain the low per iteration cost of gradient descent type of algorithms. there are actually other type of algorithms such as alternating least squares that may achieve this type of condition number independent rate, but the per iteration cost actually is a little bit higher, much higher compared to the vanilla GD type of algorithm. So we are looking for an approach that just tweaks the gradient descent a little bit, but improves the computation complexity. All right.
There is a question from the chat from Renee. He's asking what is so particular about the 1/8 weight? I think it's related to one of your.
To a slightly different constant. This is just taken from their paper. In general, with the theory, you can pick a different constant. You can do 1/4, 1/16. There's not much difference. So let me now introduce this new algorithm called that we call the scale gradient descent. If you still remember what you see in the previous slides with the vanilla gradient descent approach, there are two key differences. The first one is we now no longer need the balancing regularizer, which is often not necessary when you run this algorithm, but just you need it somehow for the convenience of the theory. Now, in this scale gradient descent algorithm, we completely drop that balancing regularizer and work directly with the unregularized loss function. We do not change anything about the spectral initialization. The only trick we do is when you update the factor matrices, instead of just searching along the gradient direction, you're going to carefully precondition your search directions in the following way. So this, first of all, this preconditioner is going to be iteration varying. It depends on where you are at the current iterates. Second, you're going to say precondition your left matrix factor X by information from the right vector. Particularly, you're going to construct this R by R matrix constructed using Y transpose Y and taking its inverse. So basically, you add a small computational cost when you compute the search direction by computing the inverse of a small rank small R by R matrix. And this is negligible compared to the computational complexity of computing the gradient of this problem. So with this in place, we effectively have this algorithm, a new algorithm that we see is basically a preconditioned gradient method. If you vectorize this set of equations, this preconditioner will actually pop up on the left-hand side of the gradient, which will match with in the general form of preconditioned gradient type of algorithm that we wrote down in the introduction. And we do not need to add any nuanced balancing regularization. All right, so since the change is really tiny, but the gain is actually pretty huge. So coming back to the earlier toy example, low rank matrix completion, you see that by plotting just on top of the previous plot, all the performance we get from scale gradient descent over the entire set of condition numbers, the performance is effectively unchanged with respect to the underlying condition number. In particular, it also matches with the performance of vanilla gradient descent when you have perfect condition number kappa equals 1. All right. So with this in mind, this really justifies or confirms the idea that this scale gradient descent algorithm indeed converge in a condition number independent manner, and with a small overhead in terms of per iteration cost on top of vanilla gradient descent.
There is another
I
question.
see there is a question. I'm going to hold off that after I talk about this slide. Right. So now we see that the algorithm actually gives us nice empirical performance. Let's try to zoom in a little bit to see why this is a good design in general. After we actually wrote down this update rule, we realized this actually have connection to some of this literature in low rank matrix optimization from the manifold perspective. In particularly, you can always think about the update rule. Even though we're doing all of these updates on the factor space, you can think about how this algorithm progress along the general low rank matrix manifold by writing out this matrix MT as a product of the factor XT and YT. And we know that this factor representation is actually not unique. You can change the parameterization using any invertible matrix Q. So therefore, a natural question is, how does the trajectory of the algorithm changes when we change the underlying parameterization of these factor matrices? And one nice property of the scale gradient descent algorithm is that turns out the trajectory of this algorithm on the low rank manifold is invariant with respect to the underlying invertible transforms you are using. And this is not a property that is maintained when you just use vanilla gradient descent. And that may also explain why, when you use vanilla gradient descent, the algorithm is very sensitive to yield conditioning. Let me look at the question. Yeah, there's some question about the relationship between this algorithm with Newton's method. So indeed, you can think of this algorithm as some sort of quasi-Newton algorithm that you can, if you do the low rank matrix factorization problem, you can see this is essentially giving you the approximation of the Newton method, but just using a diagonalization of the Hessian. There is also a question about why the additional cost is small, because it requires computing inverse of the matrix. So the computation of these preconditioners actually do not depend on the condition number. And also for this low rank matrices, if you actually write down the form of the gradient and merge it with a preconditioner, you can end up with more clear view about the computation. Basically, with the gradient, will also generate a matrix YT. And then you essentially only need to compute kind of the SVD of these factors, right? Well, not really SVTs, I would say. But in general, if this will not depend on the condition number, because its matrices are actually only depend. The key takeaway is it only depends on the rank of the matrix. The size of this matrix only depends on the rank. But the main computational cost comes from computing the gradients, which has a size depending on the ambient dimension. All right, so let me continue with a little bit on the theoretical end. One of the key challenge in showing theoretically why this algorithm actually converges at a kappa independent rate is to come up with the right distance metric as a Lyapunov function. And to do so, we have introduced this new distance function that carefully basically incorporates the impact of this preconditioning in the distance metric. That is sort of the key difference from the previous research. Another key difference is now from the analysis perspective, we can not just do a black box analysis, but rather have to do a very careful trajectory-based analysis in order to fully realize the computational benefit of this scaled gradient approach. So with this, I'm ready to present our theory. Roughly speaking, for the same low rank matrix sensing problem with IID Gaussian design, we can provably show that now the iteration complexity becomes independent with the condition number, where it will converge to epsilon accuracy on the order using an order of log 1 over epsilon iterations, at essentially the same sample complexity as the previous approach. So this makes sure that basically our approach strictly improves over the previous result by 2 al, where the algorithm probably accelerate vanilla gradient descent at essentially the same sample complexity. Right. Now, in the paper, we actually provide more general results for our scale gradient descent algorithm for a bunch of other problems, has the low rank structures underneath, such as the robust PCA and the matrix completion problems, where we show our algorithm again improve the computation cost from the iteration complexity perspective by a factor of the condition number at more or less comparable sample complexity. Sometimes it has better complexity, sometimes it has worse complexity. If you're interested in this work, we actually also published the code for this algorithm that we really encourage you to try it out, because this only requires tiny tweak in the vanilla gradient descent algorithm, but you can basically immediately see the benefit, particularly when your underlying problem is ill conditioned. So far, the only result I talk about is for the noise-free case. Just want to highlight a little bit for the setting when there may be underlying noise or proximally low-rank structures. So the key takeaway is we are not claiming scale gradient descent actually converges to a better solution than vanilla gradient descent. It just converts to the same quality solution much faster. So again, in this plot, we only show the result for matrix recovery for the same real data set I showed earlier within a small number iteration around 400, where we see ScaledGD already achieves a much lower error than vanilla GD. Now, if you run this algorithm by 1,000 more iterations, vanilla gradient descent will also achieve the same accuracy, but it just takes much longer. There is another question about, do the accuracy or the number of iterations depend on how good the spectral initialization is? Yeah, I think so. So actually, in the sample complexity, we have a condition. We have a dependency on the condition number in the sample complexity, and that is because of the spectral initialization. If you can come up with better initialization for these algorithms, they can all converge faster. There is another question about how many outliers. So I guess the question is about the robust PCA setting, where the fraction of the outliers, roughly speaking, if you just look at these comparisons, it's a little bit hard to compare on hindsight. But roughly speaking, we have a little bit better dependencies in terms of the corruption fraction compared to the vanilla GD algorithm from, I believe we are comparing with one of the earlier paper by Yudong Chen and other co-authors, where basically still I want to highlight this fraction is still depends on the order 1 over kappa. So you still see the kappa in the statistical rate. This is something potentially can be improved by using more clever strategies, such as a peeling-based approach, but we didn't go there. But this is still a better tolerance compared to the previous one using vanilla GD. Another theoretical improvement over the vanilla GD algorithm they have is that they always use they have additional projection step to preserve the incoherence property of the low-rank factors. Well, in this, our algorithm actually do not do the projection steps. I want to also mention that our result for robust PC actually do not handle missing data at the current stage. So this is basically just a matrix decomposition problem where we want to decompose a low-rank matrix from sparse corruptions. All right, so let me now just briefly talk a little bit about the generalization of this work, where we try to also handle sparse outliers in this scenario. So this just modifies the observation model by thinking about what if a small number of observations can be arbitrarily corrupted due to maybe sensor failures or malicious attacks, whereas say the fraction of the outlier can be small, say by 5% also. Now, in order to handle such sparse outliers, we can no longer use the standard squared L2 loss, but rather other alternative candidate is to use this instead the least absolute deviation loss instead, where we just try to basically minimize the squared L1 loss of the residual. All right. So one of the things that is that this now introduces the non-smoothness of the loss function. But nonetheless, we can still do the same scaling trick by just scale the subgradient using the similar preconditioners, where now the step size has to be set more carefully, either using the polyak step size or geometrically decaying step size. Now, again, comparing with some of the previous results, that we see that for both matrix sensing and quadratic sensing problems, we can again improve the computational cost by a factor of the condition number in these approaches. Okay, so the key takeaway is that now if you combine both this L1 loss and the scale gradient trick, you can achieve robustness to both yield conditioning and adversarial corruptions. Right? So with that, I have concluded the first part on yield conditioned matrix estimation. I want to just pause briefly to see if there are any additional questions before I move to the second half on policy optimization.
One quick question I had was that you use the spectral initialization, and at least for regular gradient descent, this constrains the dynamics of GD in a very particular way. What is the effect of the preconditioning on that dynamics and the connection of that with the spectral initialization?
Yeah, that's actually a very interesting question. So if we do empirically, we do see that the preconditioning actually also helps if you use random initialization. So often if you use random initialization and if you plot the errors, you have an initial stage where you see the error basically stay flat. And after a while, the error starts to drop linearly. And if you use this scaled gradient, the initial phase actually also becomes much shorter compared to using vanilla gradient descent from the same random initialization. But we don't have any theoretical explanations for that. It's actually very interesting to think about, how to think about the effect of preconditioning if we do random initialization.
And my other question is, you had this objective that had the extra balancing term versus non-balancing. Are there any acceleration effects that emerge from adding the balancing term versus not?
Yeah, that's actually a good question too. I know there are papers, not from our group, that they actually argue that balancing can help when you initialize from an unbalanced initial point. So for example, if X and Y don't have the same level of norms, then having the balancing regularization will sort of, force the factors to get back to a balanced track and get better convergence. Because again, in our work, we always use spectral initialization, and the initialization is always balanced. And as long as you always use balanced initialization, the iterates will stay balanced, and then you don't really need the regularizer there. But if you start from something that's very off, then that may help.
Thank you.
Okay, great. So now let me move to the second half, which is sort of switch gear to a new topic for me that I just started working on in the last year on reinforcement learning. And this is accelerating convergence using policy optimization. And this is joint work with my student Shicong Chen at CMU, his friend Chen Cheng at Stanford, and my collaborator Yuejie Chen at Princeton, and Yuting Wei also at CMU in statistics department. So I don't think I need to again introduce much about reinforcement learning, as is now hitting news at a sort of very regular pace that roughly in reinforcement learning, an agent learns by interacting with typically unknown environment. And among all the successes that you see in the news, policy optimization is arguably a major driver towards these successes, which is also one of the approach to reinforcement learning I would like to investigate a little bit in this presentation. In order to do so, I have to introduce some mathematical models just to set up the stage to formally model this RL problem as an optimization problem. And one such model is this Markov decision process, which sort of models how an agent interacts with the environment. So in this model, we have a state space that we model just where the environment is. So for example, if I'm playing a game of Go, the state can be just how the current configuration of the stones in a panel. And the agents will make actions from an action space. For example, where to push the next stone in this panel. And upon receiving this current state and action, the environment will push some reward to the agent, which is a function of the current state and the action. In a normalized setting, I'll just think about this as some number between 0 and 1. This is not very critical in the scope of this presentation. And the agent will be making the action according to some policy or action selection rule. Roughly speaking, you can think of this policy pi when fixing the state is some probability distribution over the action space. Okay, and the environment typically is stochastic. So after this current time step, the environment will be moving to a different state that will be determined by a probability transition kernel. Again, it's a function of the current state and the current action, right? So this is a probability distribution over the state space. All right. Now, an important question in RL is to evaluate the quality of a given policy. So imagine I have this MDP in place, and I'm sort of executing a policy pi, which gives me this trajectory of this MDP. And along this trajectory, I'm also collecting a bunch of rewards. Then I can define the value function of this policy as the discounted total reward. Okay, where the reward per time slot is going to be discounted by a factor gamma t, where gamma is a so-called discount factor in an infinite horizon discounted problem setting. And I can similarly define another quantity called the Q function, which is defined very similar to the value function, except that I'm going to fix my first action as A, and then do the rest of the action following the policy pi. Okay, so the only difference here is where you draw the first action, whether it's going to be fixed as A or following the same policy pi, right? Now, in these problem settings, the parameter gamma is kind of important. This roughly tells you the effective horizon of the problem. After a certain time point, the reward you get in the future doesn't really matter much from the value function perspective. And the effective horizon is roughly on the order 1/1 minus gamma. So the larger gamma is closer to 1, the higher, the larger the horizon of the problem. All right. Now, in a lot of RL settings, particularly in practice, people tend to enforce some sort of regularization in order to encourage the agent to explore the state space, which is particularly important when the state dimension is high. So in order to encourage exploration, a trick people do in practice is a so-called entropy-regularization. So everything is the same as the previous slide, except that instead of using the vanilla value function, I'm going to have this so-called soft version of the value function, where the reward function at each step is going to be also depends on sort of the stochasticity of the policy I'm invoking in that time step. All right, where the parameter tau is a so-called entropy regularization parameter, or alternatively temperature in some of the literature. Okay, so with this in place, roughly speaking, this will try to promote the policy to be more stochastic when we think about the maximizing this value function, right? So a general goal in this entropy regularized RL problems is you want to try to find optimal policy to maximize its value functions. If I pick the regularization parameter tau to 0, then this just go back to the vanilla value maximization problem we mentioned before. All right. So how to do optimization on this? To do optimization, we need to first get a loss function. And since I just defined this value function, but over all the states, I want to sort of start by just aggregating this over a state distribution by just crashing this in a single scalar that depends on the initial state distribution rho. Right? Then since pi is something from the probability simplex, a convenient way to deal with this is to do a softmax parameterization, so that the policy becomes parameterized by the underlying parameters theta. And then I can really rewrite this policy optimization problem as maximizing over the parameter theta for this value function, where theta is unconstrained. Right? Now, this starts to look very similar to a standard optimization problem. And then policy gradient methods is exactly solves this just using a simple gradient ascent method where you just update the parameter theta along the gradient direction of this value function. All right. Now, preconditioning happens when we think about an alternative method called the natural policy gradient, which was proposed by Kakade first in this context of policy optimization. So roughly speaking, for the same loss function, instead of searching along the direction of the gradient, we're now going to precondition the gradient using the inverse of this so-called Fisher information matrix that is defined as some functional over using the parameterization of the policy. Without getting into the details of why this is useful, so the intuition is that you want to have the nice property that locally the search direction is actually invariant to the parameterization of the policy you are using. Right. Now, throwing out just a toy example to get some sort of mental picture about the trajectory of these algorithms. Here, we're just considering a very simple setting with a toy bandit problem with 3 arms. So the parameter gamma is just 0. And I have 3 arms with different rewards. So I have, say, the initialization is plotted in these dots, and the optimal point is also plotted in dots. And on both pictures, I basically plot the flow of either the policy gradient or the natural policy gradient in the parameter space. And I have also plotted basically how the algorithm runs if you follow the flow of the policy gradient versus the natural policy gradient. Right? So without too much explanation, you can see that just from this illustration, the natural policy gradient seems to be following a more direct path from the initialization to the optimal policy. And therefore, there is potentially hope that this algorithm is indeed more computationally efficient. Okay. Indeed, we see that this type of policy gradient methods has been very successful in practice because first of all, it tries to directly optimize the policy, which is of quantity of interest. And also, you can sort of throw in a lot of flexible differentiable parameterizations, sometimes using deep neural networks, to make these problems just really very scalable and sort of can be combined with a lot of advances in deep learning. And indeed, one of the most popular methods called TRPO, it can be essentially thought as this natural policy gradient approach combined with line search. And this entropy regularization idea has also been very successful and been noted in several landmark papers in the literature. So the question we ask ourselves as a theoretician is, can we actually justify the efficiency of this NPG algorithm in this entropy regularized settings? The challenge again is because most of these problems are actually non-convex or non-concave, since we now think about maximization. Nonetheless, we were particularly encouraged by a recent line of work in the literature that tries to understand the global convergence of this policy gradient method for some control problems such as LQR and for some of these tabular MDP problems. So with that, let's get started with the particular problem we are interested in. In this particular work, we are focusing in the sort of basic tabular setting, which is sort of the first step before you go to any of the other more involved function approximation settings. And turns out that in this tabular setting, this NPG algorithm actually admits a very simple and nice update rule that you can essentially think about the policy is being updated as some sort of multiplicative combination of the current policy and the soft gradient version of the Q function evaluated as the current policy. Okay, so pictorially, you can imagine, let's say you are starting at some policy, and you can always try to evaluate this policy, the quality of this policy by writing out its Q function. And one possibility is to just update the next policy by doing a gradification of this Q function. And in this particular algorithm, you're doing this soft gradification through this exponential map. And that is essentially what you get if you set the largest possible step size. And you are basically now using the history policy at all. Typically in practice, because people use sort of the data and they don't want to be too aggressive, they're going to use some sort of combination of the history policy and the gradification. And that's where you will basically land depending on how you want to set the step size. So you can sort of tune how much you want to deviate from the current policy versus the sort of the conservative you want to have in the updates. Okay. So another very nice and interesting perspective of this update rule is that with this NPG algorithm, this active rule actually becomes magically invariant to the choice of the initial state distribution role, despite we have introduced this in setting up the algorithmic framework. And this is something quite unique when we are dealing with a tabular setting. All right, so now from the now up to the theory, because of time, I'm not going to show the entire theory, but just going to focus on the exact setting where we assume you can actually perfectly evaluate the policy, for example, through access to the model of your MDP. This is, of course, not realistic if you have a real IL setting where you have to actually evaluate these policies using data. But nonetheless, this will be a good step, particularly will sort of fit in the realm of doing dynamic programming optimal control, where you assume you have access to the models. In the paper, we do have a version of the theory where we assume the policy is only imperfectly estimated. So I encourage you to read our paper if you want to look at the results for the inexact case. But just focusing on the exact case, our theory says that for the entire range of the learning rate, we can actually ensure the algorithm actually converge linearly to the optimal soft Q function in terms of L infinity errors. And at this point, I don't want you to just get into the details of the terms, but just want to highlight that there's actually no excessively large constants in the result. This constant only depends on the initialization and the step size and the temperature you are using, and it's actually very well controlled. There's no large constants in this result. Another thing that's sort of nice is that because of now we have entropy regularization, we can actually pin down a unique optimal policy and talk about similar linear convergence to the optimal policy in this L infinity norms as well. Okay, where the rate is essentially very similar to the rate for the convergence of the soft Q function. Okay, now let's just look at a little bit of interpretation of these results. So in order to achieve epsilon accuracy for the Q function, now if you're using a general learning rate, we see the iteration complexity is roughly on the order 1 over eta tau times log 1 over epsilon. Where if you want to fix the step size eta as a small constant, and if you could basically this says the convergence rate actually become faster if you use a higher amount of entropy regularization. Okay. Now, if you use the largest possible step size, that is on the order 1 over gamma divided by tau, you see the iteration complexity essentially become constant, and effectively the effective horizon of this infinite horizon problem on the order 1 over 1 minus gamma. Now, remarkably, this result is actually showing the algorithm achieves global linear convergence from a random initialization for this highly non-convex problem at a rate that is independent with the dimension of their state space and action space. So you can have a very complicated MDP, but the algorithm still converge at a fast rate. This is pretty amazing, especially compared with comparable results that analyze entropy-regularized policy gradient descent without the preconditioning. And in this result, I won't get into all the details in these terms, but immediate impression is that this has much more dependencies with other problem parameters. And particularly, they have this interesting term that sort of depends on the minimum entry in the policy you are using across the iterates of the algorithm. And this term may have some unclear dependence with the state action space. Potentially can, in fact, have exponential dependence with the state dimension. And this indeed, again, just highlights the role of having the preconditioner in these algorithms really allows us to converge at a much faster rate that the rate is independent with the problem dimension. All right, so as an aside, I do want to just compare this algorithm with a scenario where you don't have entropy regularization at all. So in fact, this type of dimension-free feature of NPG is already observed in the prior work when they do not have any entropy regularization. Now, the benefit of having entropy regularization, even just a tiny amount, is that you can actually achieve a dramatically different type of rate, albeit for a different objective function. Okay, so on this slide, we are showing a comparison of the algorithm where we just add a tiny amount of entropy regularization, where we know from the prior work that this vanilla algorithm converges at a sublinear rate on the order 1 over epsilon, while with the regularized algorithm, we can converge at a rate on the order log 1 over epsilon. Okay, so this seems to be suggesting some sort of computational benefit of having entropy regularization, enabling fast convergence. Okay, so with the remaining time, maybe just a couple of minutes, I want to just talk briefly about sort of very cute technical idea we have underneath this talk, underneath this work. So one of the interesting things we discover in this work, there seems to be some underneath interesting connection between this optimization framework using natural policy gradient and the classical dynamic programming framework that sort of people have known long time ago in the control literature. Just to recall, we all know that this Bellman operator plays an important role in optimal control, where roughly you can think of this as an operator that applies over the Q function. If you know the model, you can recursively apply this Bellman operator on the Q function so that the Q function will converge to the optimal Q function of the problem. And what drives the success of this value iteration is that this Bellman operator has two important properties. So the first property is that we know the optimal Q function is actually the unique fixed point of the Bellman equation. Okay. The second important property is that we know if you this Bellman operator has this nice contraction property in terms of L infinity norm, so that if you apply this recursively, the error actually retract at a rate of gamma, where gamma is a discount factor of that problem. So this property essentially ensures that if you do value iteration, the algorithm converge fast to the optimal Q function. Turned out that for this entropy regularized problems, we can define a similar soft Bellman operator, which I won't get into details of this expression, but we know that we have the similar type of soft Bellman equation where we know the optimal soft Q function is also the unique point of the soft Bellman operator. And the soft Bellman operator also has this nice gamma contraction property. And with this mapping sort of measured properties in place, we can effectively show the convergence of our algorithm when we have the largest possible step size for the soft policy iteration by just measuring the proof for policy iteration, where you dance between policy evaluation and policy gradification using Bellman operator, to the case of convergence of soft policy iteration, where you just dance between the policy evaluation and soft gradification of the Q function using the soft Bellman operator. Now, for the more general case where you use a general step size, you need to be a little bit more careful and construct the 2x2 linear system to sort of check the convergence of the algorithm. But the proof is still very sort of elegant in my own opinion, and it only spares in no more than 2 pages. So if you're interested, I encourage you to read our paper for the entire proof. All right. So with that, I want to conclude. In this presentation, I have used 2 case studies to highlight the sort of significant role of preconditioning that many settings, it seems to be able to dramatically increase the efficiency of manila gradient descent methods, even for very challenging non-convex problems. In this particular presentation, I go over 2 case problems, one in statistical learning, one in reinforcement learning. I think there's certainly a lot more other problems where we can argue about the potential benefit, particular computational benefit of preconditioning in problems going beyond the scope of this presentation. I think it's very worthwhile direction for future research. If you're interested in some of the papers, you can find all these papers on arXiv and also on my website. Before concluding, I just want to thank the funding agencies without whom I won't be able to talk about all this work. And thank you so much for your attention. I'll be happy to take any of the additional questions you may have.
Thank you, Yuejie, for the great talk. Are there more questions from the audience? So you can put the question in the chat box if you want. So maybe I can ask a question while we wait for other people. So I have a question regarding the first part of the talk regarding the matrix factorization approach to matrix sensing. So I think it wasn't mentioned explicitly, but I think it's assuming that the size of the factors are given, right? Are precisely the rank of the underlying low rank matrix.
Yeah, at least for the theory, we assume we know the exact rank of the low rank matrix. Empirically, the algorithm seems to be still working if you have imperfect rank specification. I'm not sure whether the theory will still go through. You probably need some new techniques for the theory to go through.
I see.
But that was exactly the connection, I think, with the question I was asking, which is that you need to invert those matrices at every iteration. And I asked about the condition number. But if you overestimate the true rank, then those matrices will be becoming low rank as the iterations proceed, and then you need to invert the matrices. So that was exactly what I was concerned about.
I see. Yeah, so if that's the case in the empirically, you can use a pseudo inverse, and that seems to be working well. I just don't know about the theory, and I don't want to overclaim on the theory part.
So then to make precise, the theory requires exact knowledge of the true rank at the global optimum.
Right. So the theory assumes you actually to have perfect specification of the rank, basically. Which is also true for the other analysis of vanilla gradient descent type of algorithms in the literature. So yeah, it will be actually very interesting to see how to sort of reconcile this particular aspect.
Can I ask one quick question regarding to optimization? So, I mean, I'm not very much, well knowledgeable about your background, but I just wonder how actually your process is related to preconditioned conjugate gradient method classically used in the solving the linear question problem. And the second question is, your process is seems like, I'm not very clear in terms of what updating X and Y, or how you're going to actually alternate of the two components.
Okay. So the second question is easier to address. We are basically simultaneously updating these factors.
Yeah. So this means simply that you fix the, for instance, the upper equation. You just fix the Y and then you update X, and then again, right?
So you fix both xt and yt.
Yeah. Okay.
And then you update xt and yt simultaneously.
Yes. So then, actually, my first question is, it's like I'm not very expert, but it seems like it was kind of the already in linear equation domain. I think preconditioned conjugate gradient method is a very common techniques for estimating the linear.
Yeah, exactly. I'm not claiming preconditioning is a new idea. What I'm claiming is for this particular non-convex problems.
Okay.
Writing down the right precondition factors and showing they actually work theoretically to give you the to verify the empirical gain you have, is new.
Okay, yeah, thank you.
Great. So if there's no other questions, let's thank the speaker again for the great talk.
Thank you so much for having me.
Thank you. So